Hi, and welcome to our lesson 8.3. Previously in this chapter, we have created confidence intervals based on the proportion from a sample that we took, the proportion of successes from a single sample, which is a wonderful thing to do. However, it's often more common and somewhat more important sometimes to compare what happens between two samples to see if perhaps things have changed over time or whatever. So today we're going to talk about confidence intervals for the difference between two proportions. That is, we're going to compare one to another. I'd like to have you take a look at this situation. Recently, which for this context, that's probably around 2004, a poll of 29,700 households, that's a lot of households, found that 63% of them owned a pet. The percentage back in 1994 was reported as 56% for a much smaller number of households. There definitely is a difference between those two proportions, and it's a good thing, by the way. The sample size is not going to make a bit of difference in our prediction. Both of these are significantly large that will be safe comparing percentages. So obviously there is a difference in those two proportions, right? The percentages are different. Our job is going to be to determine whether that difference is statistically significant. And I'm going to put my word whether that difference is statistically significant. And we all know that that means it has to meet some mathematical criteria. Statistically significant. Right? We have to do that with math. It's not just by saying, yeah, it looks like they're different. We want to know, are they different enough that it's considered unusual? Folks, the confidence interval itself is never going to change. A general formula for any confidence interval is this. It's the sample statistic, sample stat, plus and minus some margin of error that's computed by looking at a critical z-score times the standard error of the statistic. Okay? That formula works for any confidence interval. What we have to do in this case is decide exactly what our sample stat is. We want to review our memory about, or refresh our memory about the critical z-scores, and we have to talk about the standard error of the statistic. P hat 1 and P hat 2 are the proportions from our samples. Okay, proportion of successes from our two samples. And again, the statistic that we're going for here is the difference between them. So the sample stat is P hat 1 minus P hat 2. That's what we're going to be comparing. Critical Z, just want to take a quick moment and remind you, in a confidence interval, at the 90%, if we want to be 90% confident that we have the sample stat in our interval, we use a critical Z of 1.645, positive and negative, of course, because this is an interval. At 95% level, the z-score that we use, you guys know that, that's positive and negative 1.96. And finally, if we want to be really sure, 99% confident, the z-score associated with that is positive and negative 2.576. All right, very close to 258. So we've got our sample statistic. We remember about critical Z. Now we got to define the standard error of that statistic. And folks, it is this. It is the square root of, and see, we have to involve both proportions. And we do that this way. It's the P hat from the first sample times the Q hat from the first sample over its sample size. And I would just remind you, in a single proportion, that was the standard error. Here we have two samples, so we have to do the same thing with our second sample, P hat 2 and Q hat 2, over its sample size. Okay? We add together the two standard errors and then take the square root of the sum. So that means that our formula then, so here comes the formula for a confidence interval for the difference of two proportions. It is that difference, p hat 1 minus p hat 2, plus or minus a critical z times the standard error that we've just defined here. P hat 1, Q hat 1 over sample size 1 added to P hat 2, Q hat 2 over sample size 2. All right, and that's going to be the basis for our intervals. That's how we're going to make them. So that deserves its own special place of honor. All right, we need to talk just briefly about the conditions. The three criteria have not changed. Our trials need to be binomial and random. And if you think about the pet sample that we talked, or the pet situation that we talked about, that's true. Households either have a pet or they don't, and the households were selected at random from a large population. That's the second criteria. The population must be more than 10 times each sample size. That's an and in there, not a plus. Okay, it has to be 10 times bigger than each of the sample sizes. I should put the greater than sign in there. And the sample size, all p hats, or actually all n p hats and n q hats must be greater than or equal to 5, which is a little bit different from when we did a single proportion. All right, let us see how we work this thing out. We're going to do the sample. We're going to construct the 95% confidence interval for the pet data that we had earlier in this lesson. So the first of those statistics is the now, or recently, and I'm going to call that p hat 1. The percentage there was 0.63. In 1996, so I'm going to call that then, and that's my second p hat. That was only 56%. We're going to look for a 50 or 95% confidence interval for that information. So let us begin. The first thing that we want to do is build the center of our interval, and that's p hat 1 minus p hat 2. So 0.63 minus 0.56. That's added to, plus or minus, and critical z for 95% is 1.96. Then the standard error would be 0.63 times 0.37 all over, and it was 29,700 US households. The second sample had a p hat of 56. That means q hat is 44, and the sample size there was 6,786. 6,786. Okay, this definitely calls for a calculator. I don't want to do that math in my head at all. So I'm going to ask you to take just a second and come up with an interval, and I will show you mine, and then we'll talk about how you interpret it. Okay, based on my computations, which you can see part of here, I have the lower boundary on top, and that came out to be about 0.057. The top boundary about 0.083. And now we have to talk about what that means as we interpret this thing. As we interpret this, what exactly is that saying? And remember, your statistic was about the difference between two p hats. Okay? So our interval is all positive. And if you think about that, that means with repeated many times, when we subtracted the first thing minus the second, we got something that was positive. This is all positive. So if the interval is all positive, it means the first thing is 95%. In our case, 95%, we're confident that it's bigger than the second. Okay, when we subtract, we get all positive, so the first is bigger than the second. Now you know what's coming up. We had to back up. If it's all negative, that would mean that when we subtract a p hat 1 minus a p hat 2, and we do it a bunch of times, then we got a negative. That means the first thing is smaller. If the interval crosses between negative to positive, technically what that means is there's no statistical difference between them, okay? Even though you are finding they are different numbers, there's no statistical, okay, no significant difference between them. Or you could say a valid conclusion about size can't be drawn, or something to that order. We should always tie back our intervals to the context of a problem. So we can say, based on what we did, we can say with 95% confidence that the proportion of households with a pet is greater now than it was in 1996. Proportion of households with a pet, got to get that context in there, is greater now than it was in 1966. Or 1996. Greater now than in 1996. So there you go. We've got the difference between two p hats with a margin of error. When we did the work to come up with a lower and an upper boundary, we found all positives, which means that since this is a difference thing, the first must have been bigger than the second. Okay, and so we always want to put our conclusion in terms of the context. You should include the confidence level that that you're using. Your TI 83 or 4 will give you a confidence interval for the difference of two proportions. That is, it's the stat key, stat, in the test menu. In the test menu. You want a 2 sample, let's see, 2 samp p int. I think that's how it goes. 2 samp p int. Oh, there it is. It's 2 prop z int. And it is choice B. All right, 549 teenagers were asked if it was appropriate for parents to install a special device on the car to allow their parents to monitor their driving speeds. That's becoming a little bit more common, I believe. Among the 325 13 to 15-year-olds in the sample, 50% said yes. So we're going to make 13 to 15-year-olds our first sample, and their p hat was 50%. Among the 224 16 to 17-year-olds, only 28% responded yes, and that is significantly lower. You can assume that the teens were selected randomly and were to construct and interpret a 99% interval for the difference between those two proportions. Let's see how this test works out. What we need to put in there are the number of successes. And folks, we have the total number of kids who answered the question, 13 to 15-year-old, as 325. However, only half of them, so I'm going to multiply by 0.5, half of them said yes. This test will not let you have a half a person in there. So I think that we need to just set a standard here, and I'm going to say we're going to round down, 162. So that's going to put us close to 50%, but it won't be exact. Notice that I did the math right in the line there. The second sample had 224 students in it. These are the older kids. And 28% said yes. So we're going to multiply by 0.28. We need to get to 62 kids. Again, we're going to round down. We want whole numbers of people. And that was out of 224. So that rounding is going to make us be a little bit off, but not a lot. We are asked to do this at the 99% level, so I'm going to change to 0.99 and go ahead and calculate my interval. Shows up right there at the top, which is great. That interval is 0.11664 on the low end to 0.32671 on the high end. Notice it gives us a value for p hat and q hat right around 50%, right around 28%, so we're safe there. Our job now that we have the interval is to interpret it, and we have all positive numbers, so you know exactly what's going to happen here. We can say with 99% surety that the proportion of all 13 to 15-year-olds who agree or who agree with the monitoring device the speed monitoring device is larger than the proportion of 16 and 17-year-olds. Right? And then we've interpreted, again, using the correct language. We got to give the level of confidence. We got to tie back, and we got to remember that we're talking about the proportion of all, like this is the population. As far as all teenagers in the US go, probably around the world, 13 to 15-year-olds would agree with this more often than 16 to 17-year-olds would. Very good. You've seen what we got to say about the proportion, difference of two proportions interval. I'm going to ask you to get out there and do the U-try as quickly as you can. Thanks, guys.